Welcome one, welcome all, Daniel Sheikh here. Now, initially in the previous video you saw, I was starting a series on how to classify meteorites from start to finish. And while that series is in progress, it does require quite a bit of editing because it does require a lot of educational information that needs to be learned as we go from start to finish. However, in the meantime, while this is going on, I'm still classifying meteorites in real time. So I figured, why not in this series between videos, why not post vlogs of when I'm actually doing real-time meteorite classification? And while it might be a little more intricate and maybe to some people a little confusing as to how I'm sort of going about that process, I think it's a very good explanation on the practical side of how I use equipment to understand minute details in meteorites to tell me what they are. And I think if you look at some of the vlogs and then eventually once I have my video series out, when you look on those videos, I think you can learn a lot more about classifying than rather me just either showing myself doing the procedure or me myself talking about the procedure, but not actually showing any examples of that. So I think both together are essential. So with that, I really hope you enjoy this video. I'm going to be looking at a very interesting lunar meteorite per se. And going into this video, I didn't know what the sample was. This was sort of starting from the beginning when I actually got into the room and, set up all the equipment and, started the analysis. So you'll see my live time reactions to when I first see the sample to when I'm starting to collect data. So I really hope you enjoy. And with that, let's get started. And we are home. Welcome one, welcome all. Daniel Sheikh here. Today, we're going to be classifying two meteorites, at least I think they're meteorites, using our trusty old friend, the Scanning Electron Microscope, or as I like to call it, the SEM. So first things first, I've got my thin sections containing, well, essentially what the meteorites are on the thin sections, but this is my box containing the thin sections. And what I need to do is I first need to get this onto a holder, which I'm then going to insert into the SEM, which also requires me to sort of turn on all this equipment, which I'll do that very soon. And once it's in there, we can pretty much do the analysis. So I'm just going to do a quick jump cut to when I actually load the holder into the chamber, and I'll have a video of that. And then I'll go into when I'm actually showing when I'm on the instrument. So let's do the jump cut right now. And for everyone wondering about the SEM, it looks just like this, so you can see. So let me do this again. So you can see this is what it looks like. So it's not a very large instrument per se, but there is a sort of on this platform right here. This is to make sure that any of the vibrations caused by any of the moving objects, we have a streetcar that passes over, people are walking in and out, all sorts of construction work is going on in this room. And so we want to make sure that when we're on the sample, we don't have anything disturbing this, because essentially you have an electron source, fires a beam of electrons down the column, and essentially any sort of vibrations will essentially disrupt this column of electrons going down, and therefore it'll affect your signal and it'll affect any other things. For example, when the electron beam interacts with your sample, you can get all sorts of particle interactions forming X-rays, forming secondary electrons. You can form backscattered electrons. And we have all these amazing detectors right here that can sort of look at or at least they can each look at a distinct one of those interactions and what you form from those. So our X-ray detector, or probably the EDS detector, is right here. This can sort of look at characteristic X-rays that come out of our sample as a result of essentially interactions with electrons from the beam and with our sample. We have our backscattered electron detector here. You can't really see it, we just insert it. And that's going to be pretty much what I'm using when I'm looking at these samples. So you're going to see a lot of contrast, a lot of grayscale images, and that's basically what I'm assessing to determine the texture of the sample and maybe what kind of meteorite it is. And then the X-ray detector is really what's going to be helpful for me trying to get chemical compositions of mineral phases in these rocks to essentially assess whether or not they are meteorites, and if so, what kind of meteorite group they are. So that's kind of the basics of what I'm doing when I classify meteorites. It might sound a bit complex, and it is, and that's because it's a very difficult process. I've been doing this for 6 years, and I still sometimes have trouble learning certain things and trying to keep things in my head about specifics regarding the SEM itself, but there are a lot of really useful books out there. I believe there's a book by Reed in 2005 that talks about the physics behind actually what the SEM is, what it tries to do, and electron microscopy as a whole, which involves interactions between electrons and atoms in your sample. And I could go on forever discussing this, but I would leave you to look at the book for more information. However, in terms of meteorite classification, we're just focused on this primary column interacting, forming backscattered electrons, and also forming characteristic X-rays that we can detect with our X-ray detector. So with that, I'm just gonna go back to putting the sample in the chamber, and then you'll get a first-hand view of how I actually operate the SEM to classify samples. All right, so here is the holder. So it's not a very large holder, it looks like this. And so essentially, this is my box of thin sections here, and I'm gonna be looking at these two thin sections right here. So the key thing that I always do with them is I wanna make sure that the side facing up is the side I'm looking at. And you also notice they look a little dark. That's because these thin sections have been carbon coated. So relative to regular thin sections that we look at in the petrographic microscope, once we're done doing that, we want to coat them with carbon prior to putting them in the SEM. And that's mainly because when you have electrons on a surface, if the surface isn't conductive, they're going to stick there and you're going to get what's called charging. And if you have too many electrons charging, you can get sputtering of material. If that material hits any of your detectors, you can cause a ton of issues and quite an expensive repair bill, which I definitely don't want to have. So here I've carbon coated my samples using a thin layer of carbon that's deposited by vapor deposition on top. And so how that works is I go to this sort of carbon coater right here. So you pretty much put your thin section in there. You have these two little rods of carbon with a graphite with a little space in between. You heat it up and you basically vaporize the graphite, and inside of a vacuum it's able to nicely settle onto your thin sections. If you didn't have a vacuum, of course you have air and that can disrupt the deposition process, so we do it in vacuum. So here we've deposited, this is a very thin layer. We're talking maybe, you know, between 10 and 20 nanometers, which is extremely thin for us, but it's very important that we don't have it too thin or too thick, because electron charging is sensitive to your carbon coat thickness, as well as a whole bunch of other factors in terms of when you're trying to get good counts of X-rays and other properties. And especially it affects your signal sometimes if you're doing modes like electron backscatter diffraction. You don't really want to have a thick carbon coat because you're going to get artifacts in some of your diffraction patterns. You want to keep it as thin as possible, but since I'm not worried about it for this purpose, I'm just using an X-ray detector, I don't need to worry about having a thicker carbon coat. So anyway, so basically I just put the two thin sections of interest here, and then I keep them in place with these pins right there. And then what I'm going to do is I'm going to put this copper tape on top and on the bottom. Again, this provides two things. The first is to prevent charging. You're putting a conductive metal essentially on top, so electrons are going to be able to flow freely. But also what it does is when I do any sort of quantitative analysis, you want to calibrate your beam through what's called a beam measurement. And so we can do this using the copper tape. We can have the beam over the copper, essentially do the standardization or calibration, I should say, of the beam measurement. And then once we do that, we can normalize it to what the conditions are right now in the SEM, because it varies. The beam that we're measuring isn't necessarily the same every time when you use the SEM. You can get variations in your current. That's essentially what it is. And so I can measure my beam current using this, and then I can apply it towards this when I'm doing the when I'm basically doing any of the quantifiable work. It's a little late in the day. As you can see, it's 7:26 p.m. right now, so it's not the earliest time. I'm trying to use the SEM during the off main hours when the rates do go down slightly per hour, so I try to maximize my usage at night. Although when I do it, I'm mostly just looking at a bunch of samples and it is a little late for me. But yeah, so now I'm going to show you when I have the sample coated and put into the detector. All right, so this is sort of what the setup looks like right here. So on the right side right here, I basically have my setup using this software that's called Aztec. It's very useful for getting my compositional data, and I kind of use it when I'm doing all sorts of my classification process, and all the data is stored here. So basically this is the SEM computer. Essentially here is where the sample images I take on here, and then it moves over to this computer. I navigate using all these different buttons right here to do beam calibrations, make sure that my contrast brightness settings are good. I have to align the beam. I have to do wobble, tilt corrections in my stigmators. And I basically want to make sure everything is good on this end. After I insert the sample, I have to move it up relative to where the intersection point is between here and my sample. Also, I have to insert my detector. So there's a lot of things that I need to do here, sort of maintenance first. As you can see, this is sort of our status bar here, and these are sort of other things I use. And then once this is all good, then I can finally begin taking images and getting chemical data from this computer. So here's our essentially complete material here that we're going to insert in here. So we have our sample ready to go. So this is essentially what the SEM looks like when you open it. So this is our stage right here. This is another sort of detector holder that we don't need, so I'm going to remove this one. And then I need to rotate this to be here, so let me just show you how that works. There we go. And that looks to be a little off, so I'm going to go back the other way. It's a little hard doing this with one hand, but I'm going to try my best. Okay, that's about parallel. And so now what I'm going to do is I'm going to take this and I need to line it up like that. So to do that, I use my other hand to hold here, and then I sort of do this. Make sure that it's nicely settled and it's not moving, which it's not. And I push it in like this. And now I have to pump back up the vacuum. So initially I vented the chamber. So I brought it up to air pressure. Now I have to room the pressure that's, it's a little late in the day. So basically now I'm just pumping it back. I'm pumping down to high vacuum settings. So I'm essentially going to extremely low pressure. So yeah, whenever you pump the chamber, you're pumping it down to vacuum, so you're decreasing pressure. And then whenever you're venting, you're going back up to essentially the pressure, the ambient pressure in the room. Otherwise, this door wouldn't exactly open, right? Because you have to get pressure equalized on both ends. So anyway, so it's in now. And so what I'm going to do here is put some crosshairs. And I'm going to show you essentially how I do the initial calibration. So the first thing is I always try to line up the sample holder right here. Let's see. Other way. Okay, perfect. And then now I'm going to do this. So now we're moving it up. And the working distance, or where it says WD, we want that to be a set number. We want that to be 8.5 because we're calibrated for quantitative analysis at 8.5 millimeters. That's essentially where our focus is. How we do the focus is by changing the working distance. Or you can just change this knob right here called focus, but I try not to touch the knob because I want to keep it at exactly 8.5. But if I do need to do fine-tune focuses, I'll do that. All right, 1 second. Sometimes you have to change this tilt control, so let me just put that at 0 and not have to worry about that. Perfect. So the same axis that controls this sometimes also controls tilt, so you want to make sure that you don't accidentally tilt left or right, but you can fix it by looking at your settings right here. So if the number changes, put it back to 0. So that looks to be a good height, so I'm going to remove my crosshairs. And now what I want to do is I want to insert my EDS detector in here. So let's see, you're going to see it, it's right here. And then watch the magic. So the detector now is going into the chamber. You can hear that click right there. And if we look here, there it is. It's going to go right to about here. And we can bring in using this, basically. So, all right, that's perfect. Okay, so now that's good. I'm just waiting for it to get to high vacuum. Once it's at high vacuum, which is what we're waiting for right here under vacuum status, then we can actually start the instrument and I can show you exactly how I do the setup. So should start in maybe a minute or so, so I might as well just wait on here. Let me just make sure everything else is good. So I'm checking the accelerating voltage. I'm also, let me just do this, making sure that I'm at the right settings right here. Okay, is it high vacuum? Let's see. Yep, going to high vacuum, aperture settings. I want the aperture there. High current, that's all good. These are just all calibrations that I make sure that are good whenever I do my analysis. I am set on optimize right here. I'm on the right sample. Sample's inserted. So yeah, we're pretty much ready to go. We just wait for the it to reach high vac, and we'll hear a noise right there when it's ready to go. It's pretty distinctive. Sometimes it's a little I get tired at night, and you know I put the sample, and then the noise just wakes me up. So honestly, it's like a pretty cool alarm clock in a way when you hear that kind of sound. So yeah, those are nitrogen. Yep, it's over there. Gas cylinders. There they are. And we're just gonna wait. I should be starting anytime soon. Just sometimes I check just to see. Still pumping. Okay, there we go. It's gonna make a sound soon. There's like a certain sound that I hear whenever I know it's gonna be ready. And sometimes you can also just look at the system vacuum. So we're at what, 8.1 to the -5 torrs. It's 10 to the -5. Yep. I mean, so we're going pretty far down in pressure. I think it's, I don't know if it's, there we go. All right, so it's about 7 there. That's good. Okay, so we're ready to go. So let's go back to here and let's start up the instrument. So here I hit gun and I turn EHD off to EHD on. So now the electron beam is in full operation. And it takes a while. There's like a bit of a setup right here. Yeah, see here, I reached the tilt control limit. So when I was moving this, I kind of tilted it a bit, but it's now back to 0, so we're good. And then this is essentially the beam. So now we're getting interactions. You can't see it on here because obviously not with this sort of a view, but let me show you an angle where we can see the interactions. So let me turn on this. All right, and this is where the fun part begins. This is essentially where I have to do all the calibrations now. So first thing first, I want to make sure my focus is at 8.5, which it is. My brightness and contrast seem to be a little too high, so I'm going to drop both of those. And it looks like my scanning speed is long. So the higher the scanning speed, essentially the better the resolution, but it's not going to raster as quick. It's going to raster slow. And so you're not going to get so every time you move, you're going to get sort of a lag. So I always try to keep it at a low enough number where when I move, it's consistent. So like, here's my sample. And so if I just move around with this joystick, so if I do this, you'll see I'm just moving. So essentially what I first need to do is I need to focus on the samples. So let me see, let me find an area that's reasonable. Maybe something like this. Okay, that's like that is good. And let me center it. This is called center point. And then let's just sort of focus this a bit. So I'm doing what's called reduced. You make a reduced window so the rastering area is smaller, so therefore you're not waiting on the whole thing to load. And you can do your, essentially affect your focusing through here. So I'm not going to change my focus. Like I said, we got to keep it at 8.5, but I can change my Z, which is essentially the distance between that stage and where the end of the instrument was. So I'm doing that. You can see it's getting in focus. That's good. By the way, the mode I'm using is called secondary electron imaging. So secondary electrons are produced when the primary electrons generated by the electron beam interact with electrons in your sample, and they knock off electrons from inner orbitals. And so, well, they can knock off electrons from anywhere. But in the case that they do knock off electrons from inner orbitals, electrons from a higher shell go to fill in that hole, because essentially you want to essentially reduce, and you essentially want to get back to the ground state, because then you're at it. I think it's called an excitation state, and so you want to get back to the ground state of where those electrons are, and by doing so, an electron fills in the hole of the orbital that initially electron was lost from, and so you produce an X-ray as a result, which is characteristic to what kind of atom you have, and that's essentially how that works. I have to reread the book because I kind of forgot a bit on that, but for the purposes of this demonstration, I'm just showing you that we get secondary electrons, and we can essentially see into our sample, so we can get essentially almost like a view of what our sample would look like just by electrons interacting and being picked up by detector. So there we go, that's in focus. And so you can see this is what our sample looks like. So that's pretty cool. So we're at about 962 magnification, so 20 microns. That's, I believe that's thinner than the width of hair. Maybe it's almost at that. I'm not 100% sure. I know it's close to that. So that's, I mean, these are very small objects. Let's just put it that way. They're sub-micrometer. So there's that. And let me, okay, so I did that now. So now let me go to a further point here. Let me go to this small point right there. Let me go back to scan speed 4. And then now I have to go to a really high magnification. So I'm going to about 6.5. And now I'm going to do what's called a wobble correction. I want to make sure that this little object, if I bump my wobble up, that it's not moving too much. And this is always the part that I have the most trouble with whenever I do calibrations on the SAM and setting up, is this wobble. It always affects me. I spend like way too much time on this thing. But let's see. It looks to be going northwest, southeast. So let me just change this. What's that? Minus 6.2, 5.9. All right, let me put that on. That's minus 6.2. That's okay, I guess. All right, so I'm gonna stick with this for now. If it gets bad on the imaging, I can always change it, but I don't think it's too big of an issue since I'm not going too far down. So let me keep it at that. Let me do the stigmators now. Okay. So stigmators, again, were essentially, so when you have stigmation, your electron beam as it goes down, instead of forming a circle, you're going to get more of like a ellipse. So you're trying to keep it as circular as possible. Otherwise, you're going to get distortions, as you can see right there. You see when I do this, you see how it gets blurry? So we're essentially trying to reduce that and get the best quality images we can. So let's do that. There we go. That's okay. All right, and then now that I'm good, I am pretty much all set here. So let's go back. And I'm going to save this as my sample number, like that. Actually, that was not, it was completely opposite here. 67. There we go. All right, cool. So that's good. So that was the first sample, and then now let me navigate to sample number 2. So I'm just moving across the first one here. Now I'm entering the second thin section. There it is. You can see there's the border right there. And should be entering it soon. There it is. Okay, so you can see it has a different texture from the other one. This one has more of a coarse grain texture. You can see there's 2 colors right here. So it looks like, well, obviously I'm not using secondary electron when I do my analysis. I just use it first, and then I use backscatter electrons, which provide more of a density contrast. But secondary electrons can also give you some information on the density. We mostly use those for stuff like superficial features. So these can give you, you know, if you have contrast in, you know, changes in elevation, topography, like very minute details. But it sometimes can also be useful for some density differences, especially if you have a Faraday cage and you set a certain electron bias to give you, to essentially accentuate what kind of secondary electrons you get and stuff like that. But basically, you'll just notice there's 2 colors here. How about that? So that looks pretty good. All right, so I'm going to call that, this is 1672. All right, so I'm going to go back to the first one. So I'm just saving these as points so I can always navigate to them later. And then now I'm going to get to that copper tape that we initially had when we put the sample in. All right, so you're going to see it's going to get very bright. Yep, there it is. Lower the contrast. That's a little too much. A little more. There we go. Now I'm going to zoom in somewhere. That's a little too far. Somewhere about here. See all these little dark spots? We want to go somewhere that's free of them. So let me see if I can find somewhere here. All right, it doesn't look perfect here, but maybe this, or at least minimal. Let's try somewhere here. All right, we'll try this and see. So now let me just focus. So again, just making sure that everything is in focus here. There we go. Now it's starting to get in focus. Now it's going out of focus. Right about there is good. Perfect. Okay, and now for the first time, we're actually going to use this computer, and we're going to do our beam measurement on copper, and 5 million counts. Let's go. All right, there we go. So this is our energy spectrum here. This is in keV, or kilo electron volts, and these are energy peaks, or first excitation peaks for specific elements. That's what this, one of these two things can essentially tell you. And copper's K alpha's peak is here, and K beta peak is there. That's essentially where you want to see that beam measurement lined up with perfectly. That's good. Measurement's okay. Let's run another one. And then that's saying how many counts we're getting. So input counts, output counts, and then dead time is essentially when you're measuring X-rays with the X-ray detector. You're not going to pick everything up because X-rays are a continuum. You're sort of measuring a large spectrum of X-rays that keep on coming in, and so by the time it takes to process these X-rays and know what they are, you've lost some data because X-rays were going in during that time. So we call it dead time. So if you have a high dead time, that means you're not exactly counting, significant amounts of X-rays. Versus if you have a lower dead time, at least your processing is okay. So you want to keep a dead time somewhere in this range. That's kind of where the green is. So I tend to follow that. See, it says it wants working distance 8.5. That's where I'm at. Do quantitative work. Accelerating voltage. It's essentially, if you want to view it as like the velocity the electrons are traveling down the column, and then the electron current is essentially how many electrons you have there. So they're kind of two separate things. In SEM, we don't worry so much about current. That's if you're on a microprobe. Then you want to make sure that you're setting things at stuff like 20 nanoamps of current, because these are normally values that are used in literature. And when you change your current, you're changing how many electrons there are that could interact with your samples, and then that changes things like counts, and it affects stuff like standardization. Essentially, especially if you're measuring intensities of X-rays for certain elements. So always good when you do any microprobe work to know what the beam current is. But for this, we're not too focused on that. But the accelerating voltage is important for this. It's going to affect your interaction volume, and essentially is dependent on what the sample properties are. So what kind of material you're looking at. If it's iron rich, magnesium rich, silicon rich, a lot of that stuff is affected by accelerating voltage. All right, so we're good to go. So calibration is successful. So now let's go back to our sample here. So we're all good. And let's go back to 1671. Okay, and now we're going to do the fun part. So now we're actually going to go back to camera. Let me just hit this camera. There we go. Perfect. There it is. All right, and now I'm going to get up and I'm going to insert the backscale electron detector. Before I always do that, these are nitrile gloves, so I have to discharge any sort of static electricity. I always grab that handle. And then here now I can insert this, so I just hold this like that. And I just push in the detector, make sure it's in, and there it is. That's the backscale electron detector right here. So electrons in the backscale detector are different from secondary electrons, because backscale electrons, instead of electrons coming down and knocking off electrons from your sample, and then those electrons get detected, these electrons are just electrons that interact with your sample, and they undergo essentially more of like elastic type interaction. So they elastically interact with the nuclei of these atoms, and then they're later scattered, or elastically scattered back up, or they're picked up by this detector right here. And this is essentially the higher the atomic Z of your sample, so the larger the nucleus, which you get for elements that have relatively large atomic masses on the periodic table, like iron, versus something that's relatively smaller, like sodium. The higher atomic mass nucleus, or the nucleus with more protons and neutrons, so essentially elements that have high Z, we call it Z contrast, they are going to give off more signal, because those electrons that interact are more likely to scatter upwards, so their elastic scattering or backscattering coefficient is higher. Therefore, you're going to get more signal at a given point, and the signal that's measured is by grayscale. So the more signal you get, the higher the number, and that's assigned to essentially something that's very bright versus something that has no signal, it's dark. So essentially anything that's bright has higher atomic Z, therefore it's more, heavier if you want to view it on a density scale, it's more dense. And then anything that is darker in color has a lower average Z, and therefore it's less dense, or at least the material on average is less dense, if you want to view it that way. The atoms are less dense. How about that? Okay, so now we're going to go to BSE, and we're going to see how everything works here. And give it time to work. Okay. So let me get at, let me do something like this. Actually, let me find a better area here. I think this area is a little hard to see here. Let me try this area. Okay, here we go. This is a good area right here. So let's get this in there. So I'm doing what's called an auto level. So I want to make sure that I get good brightness contrast between the mineral phases. So let's see here. What am I at here? Okay, so I definitely want to increase my contrast here. There we go. That looks way better. Something like that. Yeah, that's good. Okay, so it looks like I've got some mineral phase here, some mineral phase here, and then this other one right here. So I have at least 3 that I can see. All right, you know what? This actually is a good spot. Why don't we get some points here? So let me first zoom in here and just make sure that I'm in focus. I think I am, but it's always good to just check. So 8. There we go. So now we're in focus. And then now that that's good, now let's go over here. I'm going to go to map, because I'm going to do a map here first. So I'm going to do a chemical map of this area. And first, let's do a backscatter electron image. So we're taking an image of this, and that's what's loading right here. So while this is loading, let me just talk a bit about the software here. So essentially, I'm following a workflow where I take the image, and then what I'm going to do is I'm going to do a false color electron map. So basically, I'm going to measure the X-ray intensity at every point, and essentially pick up those characteristic X-rays for a lot of different elements. And it's going to map the elements. It's going to tell me, or map the area. It's going to tell me where the elements are in this sample. So where's my magnesium? Where's my silicon? Where's my iron? Where's my calcium? Where's my titanium? Stuff like that. And it's basically mineral phases are essentially minerals by definition. You know, they're if you want to view them as mixtures of elements in different quantities, you could do that. Although minerals have very specific definitions and 5 main criteria for those. But essentially, the elements are distributed differently in different mineral phases. The proportions of the elements in mineral phases are going to reflect the intensities of those X-rays. Therefore, you're going to get a variety of colors for your mineral phases. I think the best way to sort of discuss that is by showing sort of what it would look like. So let me just hit this, and then yeah, so I'll click that. And so now what's going on is for all the elements that I have, it's picking up those K alpha energy peaks, and it's basically plotting it over the area that I already have. So it's basically going to just tell me where the elements are, and it's going to give you a nice colored map, and anything that has these specific elements are going to be colored according to that. Combinations will be a color that's mixed of those. So we'll just let this stay on this for a while, and then we will see essentially what comes out of it. Right away I can see we have an area that's like this, that's relatively, looks like it's maybe rich in silicon. We have an area here that's a little green. This might be rich in some magnesium, and my guess is this is going to be rich in material that's blue. That's my guess, but it could also be something that's a little yellow as well, yellow and blue. So we'll kind of find out. We do see some variation here. This does look to be a little different from this, maybe less magnesium. So right away when I classify meteorites, I'm looking at in meteorites, because of the fact that we're not on a body like Earth where we have lots of water that can form all kinds of other mineral phases, right? You have a bunch of clays that you can form, you have amphiboles, serpentines, those kinds of phases. When you don't have water that can get really into the the crystal structure of a lot of these mineral phases. And you also don't have to worry about the fact that plate tectonics continues to recycle and form new material on Earth. And a lot of these bodies that come from asteroidal parent bodies, they're not exactly that altered compared to what they were originally. So therefore, you can view them from some bodies as being somewhat primitive, others as being more primitive. But the word primitive in itself can also be used to define different kinds of minerals, like chondrites people call as primitive meteorites, and you have differentiated meteorites, which obviously can't be as primitive, but primitive compared to what is sort of the point. If we're comparing it to when your accreting material in this initial solar system and all that dust was settling to form, accreting together and forming parent bodies, if you want to say primitive relative to that, chondrites are primitive. But if you want to say primitive compared to the fact that you form igneous lithologies and then you don't get much disruption afterwards, you don't get much remelting, stuff like that, then you can consider some achondrites primitive. It's really dependent on what you're comparing the scale of primitiveness to. So, but anyways, this sample looks like it's got let's see, it's a very fine-grained matrix. It's almost like you have a melt. I think that's plagioclase. You have a melted plagioclase, and then you have olivine subhedral sort of like grains. It's almost like a porphyritic kind of texture, but almost more like you have like skeletal. I think that's skeletal clinopyroxene right there. So very interesting. You have some weathering products right there. I think that's a chromite, is it? Looks like it's got the color for a chromite. So yeah, very, very useful to get maps like this. I'm just going to hit stop really quick. I think it's going to run one more pass, and that's okay. I don't really need to run the full pass. It does 4 passes. I tend to run sometimes 1 or 2, but we'll just let that keep going. All right, so right away, first observations, I see olivine, I see pyroxene with varying compositions, I see feldspar, I see some troilite in that little olivine right there. I think I see metal and chromite. I don't know what that is. That could be Novospino. This might be a lunar meteorite. That's my first guess, but you never know, right? Sometimes, looks can be deceiving. Even something like this can be deceiving, and you can even think it's a meteorite, but it ends up being something terrestrial. So really here, I don't know. I think I need to get compositions of these olivines. I need to check in the feldspar here. I want to see what this is. I think it's chromite. Let me see. So I can actually look at the individual elements here. So yeah, chromium, iron, chromite. Chromite also has titanium. We can see it's zoned. It has a depleted core. It goes to the rims. That does reflect the fact that the melt probably became more titanium rich during the fact you crystallized this. So obviously if you want to view it as more incompatible, I'd imagine the phosphorus in the matrix. Yeah, that makes sense because you didn't put it into a phosphate. Yep, silicon, sodium more in the matrix makes sense. What about potassium? Can I even get a signal? Yeah, I can get a slight signal. That works. All right, so I think this is lunar, but we'll find out. So I'm going to hit point ID now, and I'm going to hit acquire spectra. And now, this is sort of my favorite part. I'm going to zoom in on the sample, and I'm going to draw these little boxes right here, these little rectangles. This is essentially where I'm getting my chemical data. So I'm telling the X-ray detector, all right, raster over that small area right there. And whatever X-rays come out, I want those to be picked up. And I want to see what concentration of elements are in that area. And so rule number 1 has to be in a mineral phase, so it can't be hitting a grain boundary, it can't be interacting with other things, no fractures. You want to get clean mineral here, otherwise any contamination, and you're not going to get a good stoichiometry on what your chemical composition is. And I'll show you what that means in a bit. So a couple of these olivines, another one of this. Looks like a sulfide there. This might be a chromite. I don't really want to get it, but sure, I'll just get one. Why not? And then let me get some of these pyroxenes real quick. This looks like it might be too small. All right, let's maybe do this area here. Let's try that. Some more magnesium here. So zone pyroxene for sure, which does support rapid crystallization from a melt. I imagine you form the olivines first, and then you probably form pyroxene later. So maybe the olivine was the liquidus phase. So how you form these big chromites, I mean, it's easier to nucleate more grains if you already have a grain that's nucleated versus forming grains, right? Because you're delta G, right? You want to get back to equilibrium, and so breaking apart during nucleation versus forming enough
to get a nucleated crystal, right? You always have that going on. So I don't know. So let me just make sure. Let's see, I got 13 points here. Let me get one more here, and then I'll do one more of this, and we'll see what we got here. All right, so olivine for sure, I can tell from this. Let me see this. Wait a second. Hang on, that's not a perfect olivine. Okay. That's very interesting. Okay, that's a good olivine. Okay, so I think my first point was just not good. All right, so that looks pretty good. And let's now check and see. Okay, it's 7 out of 28, so that's about 25 on the phthalate number. That's just iron, molar iron over iron plus magnesium. We use atomic percent for any sort of molar things. Atomic's always 100, because by default, it's the atomic makeup in moles or molar percentage. And let me see something right here. This divided by that, that's going to be a little above 73, so it's probably going to be more towards 78 or 80. So the iron manganese ratio is very distinctive. On Earth, on the Moon, on Mars, you get different ratios. On HEDs, you have different ratios of your iron manganese ratio. So basically, this is consistent with something that's lunar. But obviously, we're not just going to check olivine. We have to see other minerals. So I'm going to look at feldspar. And here's a feldspar right here. You can see, okay, that's consistent. The reason why I'm not getting a sum of 5, which is what you expect, is because I'm setting my number of oxygens to 3. So I'm normally just, for pyroxenes, I would expect 2 cations, and then the 3 for olivine, I would expect, if I do 4 anions, I expect 3 cations, and for feldspar, if I expect 8 anions or 8 oxygen, I expect 5 cations. But here I'm just keeping it at 3 for all 3 of them. So I've sort of memorized for olivine, I would get 2.25 if I go 3 instead of 4. For feldspar, I'd get 1.87 or 88 if I use 3 instead of 8. And then for pyroxenes, of course, I would get 2. So it might look a little weird if you're used to seeing this from the perspective of different minerals, but it doesn't change much. But I'm just trying to see that, yeah, this is a calcium-rich feldspar, very low in sodium. And then if I get the AN number, we're looking at 7.5. Yeah, this is lunar. So I'm getting lunar values on feldspar, lunar values on olivine. So yeah. Congrats, we have a lunar meteorite. It's that easy. You can tell it very well with this. And unlike something like a hand specimen or anything, the chemical composition does not lie. It is essentially saying this is what your sample is made of, and it has to be this. Now, could you say, well, could there be something on Earth that mimics something of this composition? And normally I'd say, yeah, you could get feldspar with AN94, on Earth. And you go to a terrestrial massif, right? You have those anorthosite layers. But then you're like, well, I get olivine in them like this. And then you're like, that's a little weird. You get chromites. But then you get stuff like this, and it's like, wait, that's iron sulfide. That's troilite. You don't get those in Earth rocks, right? You get other kinds of sulfides like pyrite. So when I see all this together, I know right away this is lunar meteorite. I can tell by this feldspar that this is masculinitized. This is amorphosed. This is masculinite, not crystalline feldspar. So it's been, this might be a crystalline melt breccia, as my guess has seen shock deformation, which is probably why we get troilite in here. I imagine we have metal. Maybe that's what this is right here. Let me see. I can check. I gotta be on maps here. Also, if I'm speaking too quickly, I apologize for that. I'm just very used to sort of going through different things. But if anyone has questions, feel free to comment with those, and I'll try to reply. Let's see, titanium. Is it? Hang on, let me do something like this. All right, doesn't look like oval spinel. Let's do this. Okay. Yeah, let's get a point. Why not? Just to see what that is. Sometimes if I don't, know 100% what it is, I just get a point. So where are we at? 10, 11 right here. So this is a pyroxene. Maybe that's what it's... No, sorry, not that one. It's 11. So that looks like a pyroxene, looks like a pigeonite, a little bit of titanium, a little bit of chromium. That all makes sense. Let me go back to 11 here. So if you want to know what a pyroxene looks like, you're going to get some that's 1.9902 if you assume 3 oxygens. Good totals, right? I mean, these are pretty good. And then let's see if I do an iron manganese ratio, that's about what, almost 50. That's very consistent with lunar pyroxenes. I could even do this in APFU, but I'm just doing the straight up ratio. And then let's say a little bit of aluminum, quite a bit of aluminum there. That is interesting. I guess if you rapidly formed it, you'd get some aluminum forming in there. That would make sense. Having this much titanium, I guess, makes sense too. Yeah, so let's see. Okay, another olivine here. Olivine looks equilibrated. Another feldspar here. That looks pretty good. So, yeah, so this is how classification works. We just get a bunch of points. We get mineral compositions, and we put them into the Miracle Bulletin database. That's really all there is to it. You know, we take lots of nice and pretty images to find out what the textures of our classes are, but really we're just seeking these mineral compositions. That's kind of the end goal here. And once we have that and we have everything established, we can do a write-up. We can say that this is a lunar meteorite that has a, I mean, to be fair, this almost looks like a, well, I have to check to see if the texture is consistent everywhere, but if it's mostly feldspar with olivine, that's a troglodytic, you know, melt breccia type texture, which means that if you had a troctolite in composition and you melted it and then, you know, you cooled, you know, you'd form probably either, let's use an olivine or feldspar the liquid is. It does depend on your bulk composition, but you get one and then you hit the cotectic, form the other one, and then you know, hit paratectic. I guess maybe that's why you're getting pyroxene. So you have some chromites here, so maybe these are remnants. You know, that's something I'd have to check, but yeah, so these are all the thoughts that go in my head when I see these samples. And yeah, so obviously I can't, you know, this is a very small area, so this won't tell me that this lunar meteorite is just what it is from this one thing. I have to go to other sites. You know, you have to get a representative sampling of the sample. I can't just get 2 points and call it a lunar and that's it. That's not the right approach to classification. You need to go around the sample. You need to see what the classes are. What, you know, is there zonation? What's going on in this sample? So let me actually see what 16 is. Aluminum, magnesium, chromium, iron. This is a spinel. It looks like a chromium spinel. It's too small, so I'm picking up silicon and calcium from the feldspar, but, you know, but it is a chromium spinel, which, you know, you could get also. This got dark. This sometimes happens here. Let me just raise my brightness up. There we go. All right, let's go elsewhere in the sample. Oh yeah, right away. This is a crystalline melt breccia, and this looks to be a troglodytic melt breccia. I mean, just look at this texture right here. You can see, wow, look at this. Let me try to get like a something like this. I'm gonna get a zoomed out map actually. Maybe a little more here. Let me do 150. I want to get that texture in this. Let me do this. Let me do that. Let me make sure I'm getting it, you know, nice and good. Okay, there we go. All good. On focus. Always take your images in focus. You never want to do it when it's not focused. It's going to look really bad. You know, so let me actually do 200 mag. I don't really like the, actually, let me go further. I don't really like this. Whenever you're looking at very fine grained things, it's so bad when you use a low mag. So I'm going to go with 300. But I also want to get these things in there. And I also want to get that little grain that I kind of missed there. There we go. So something like this isn't bad. I can actually get points from this. So let me run another map here. And let me just run another map here. There we go. So we'll get the BSC image first, and then we'll get some maps. So yeah, it does look like we took a troctolite, right? That actually looks like a troctolite right here, right? That looks like olivine, very fractured. There's a blocky feldspar. Maybe that's chromite. I mean, sulfide. Maybe there's melt inclusions on olivine, right? Typical with MG Suite material. You broke it up and then you melted it, and then that's like a remnant clast, and maybe this whole thing was like when you crystallized around the clasts. That could be why you have these sort of crystals that are aligned like this, right? These are things that kind of, again, when you're classifying meteorites, you always have to consider what the sample could be, and you always have to think about different scenarios in your head. So let's take a look right here. Oh yeah, look at that melt inclusion right there. So we had some melt inclusion, that olivine. And what is that, pyroxene that you form from the melt? Oh, symplectite. Look at this. So these are actually really cool in these troglodytes. You get these chrome pyroxene symplectites. Very cool. If I had done a low mag, I wouldn't see this. So yeah, so this is pretty good. And then we have this feathery texture. I wouldn't, maybe it's not a troglodyte melt breccia, but because I mean, it seems like maybe there's a little more than 10% pyroxene. I don't know. I'd have to check. Let's see. Let's do another map. All right, just let that go for a bit. So lunar meteorites are kind of my specialty for classifying, not necessarily like in terms of, you know, just, well, I mean, I guess so. So lunar meteorites are part of my PhD research. My research is focused on looking at unusual lithic clasts in different lunar meteorites and assessing their petrogenesis and shock deformation histories. So for me, I've been focusing on dunites. I've been focusing on pink spinel anorthosite, felsites. I've been looking at anorthositic clasts. I might even at some point be looking at these troglodytes if I look at spinel troglodytes. But really, I'm just trying to understand, you know, when you're forming these breccias and you're forming these meteorites, right, you're disrupting and you're creating all sorts of physical, chemical modifications of these initially pristine clasts. And look at this, all of a sudden it's been altered, it's been broken up. You know, you might have, if the melt around it's hot and this stays warm, you can get diffusion of elements, so equilibration. You can get all sorts of processes in these things, and it's important to understand, you know, what effect each of them has, because a lot of you know, studies try to look at, you know, clasts and say, is this pristine, is it not pristine? Evaluating pristinity is a very difficult thing. I've at least noticed while reading a lot of materials on lunar samples. So yeah, it's pretty cool. So yeah, we can see we got some sulfide here. There's a chromite. This is our summage right here. Let's see what's in there. We got, I'm guessing, high calcium pyroxene, maybe low calcium pyroxene or melt, and then you have your chromite right there. So there's just some symplectite. So that's pretty cool, right? This is Mg sweet material. It's pretty cool. Obviously, your symplectites, right? There's different papers on different types of symplectites. Some of them people think formed by garnet, right? That underwent decomposition as this thing was excavated. Some other people think that some of them form just by other assemblages that interact with impact melt or interact with fluids. So there's different interpretations on how you form symplectites. So one of the cool things about classifying meteorites is we find weird things and we're like, hey, why don't we remember where we were at and do research on this in the future? So there, maybe that's metal there. That's maybe that's sulfide. I have to see what that is. Could be just some thing with, yeah. Okay. Looks like we had some zonation in that olivine, so maybe it's not all the same thing as I initially thought. So that's good. Let me stop that right there. Let me actually get some points now. All right, let me just do this now. I think this got some zonation to it. You can see that the more green is the magnesium, it's getting a little more iron rich here. I might not add too many points, but I want to see where the, you know, how it's zoned here. Something like that is good. Let me get a couple points here. No need to get the chromite. I already kind of know what the sample is. Oh, wait a second. Is that spinel? Do we have a pink spinel troglodyte right here? Hang on a second. I actually... Yeah, it looks like... Let's see. I actually need to do research on these things. Great. Pink spinel troglodyte class in lunar meteorite. How about that? I'm doing research on pink spinel anorthosite and we have a PST right next to it. That's really cool. Let's get some more of these olivines here. See, sometimes you're just doing classification and you find interesting stuff for research. How cool is that? All right, got some feathery pyroxenes here. Let me try to find a good one. I think this is okay. Let's see. That seems a little risky. Let's try something here. Perfect. All right, I'll try something else there. So, yeah, pretty good. I'm getting a lot of different. See, the problem when you use this low mag is you really can't see the small stuff. So I have to zoom in all the way, and it can get a little difficult sometimes when you overlay these chemical maps. You get all these little green dots. That's just from the pixel size, and it's not exactly the prettiest. So, all right, let me get just a few more. I know I've already been getting quite a bit, but just something like that. And then that, and then one more feldspar here. Let me get one more pyroxene. This works. Let's get that. Let me get a magnesium pyroxene. Like that. There. Perfect. All right. A lot of points, so this will take a while. Normally it's about 2 points per every minute, or 1 point per every 30 seconds. So I try to be efficient with my timing. I don't want to get too many points if I don't need them, but I don't want to get too little points where I have to feel like I have to come back later. So, all right, let me get that third spinel. Why not? Yeah, sure. And let's see. Let me get one more feldspar here. There. Cool. So we got 44. So yeah, that's basically how I classify meteorites, and I would have this as probably a lunar troctolic melt breccia. I mean, that would make sense. So I have to obviously think about that. So I'm going to keep going around the sample, finding more, but I think I'm going to end it off here. I think I've been sort of rambling on for a little bit too long, and I don't want this to be over an hour in total. So hopefully anyone is able to get something out of this, is that meteorite classification is a very important part of science, and every time I look at a new meteorite, I always learn something. I always find new things. Like today, I have spinel, right? Pink spinel, and this looks like a pink spinel trochlite class, which I actually haven't found pink spinel trochlites. It's weird. I found spinel rich class, but not a pink spinel trochlite, which are sort of the staple in lunar science for samples having pink spinel in them. So it's always cool to find new things. And I found some plectites in that class too, so even better. So yeah, so that's it for today. I'll try to get, probably next time I go on, I'll try to do another recording session or something like that. It's not going to be very professional in the, the camera quality. You kind of see it wobbling a bit because I'm holding it, but at least it's better I get something out than not get something out. That way we all learn something together, and everyone, of course, you get to see sort of how I do my classification process. So anyways, that's everything. Thanks for watching, and Daniel Shake signing out. Bye.